Good morning, students. Today's topic is from potential energy and conservation of energy. It's a basic concept that every student must know. The lesson goal today and the concept I was referring to is conservative force versus non-conservative force. Now, our aim today is to understand, what is the meaning of this word conservative force. And naturally, if we understand conservative force, we should be able to understand what is a non-conservative force. So let's talk about conservative force and non-conservative force. I will speak about the concept first, and then we will talk about this numerical which you see in front of it. We will try to solve this physics problem so that you immediately understand what I've explained you through the lesson of distinguishing between conservative force and non-conservative force. So let's get going on this and let's start. All right. So let me just give you a perspective on what we're talking about. So now in the chapter of work, power, energy, potential energy is very important, and conservation specifically is very important, right? But how do you know, the about this conserved energy? So before you reach to that level where you talk about conservation, you have to understand what are conservative forces. Okay, conservative. I hope this is visible to you. If it is not, I can still change the color to something which is more bright. And there you go. All right. So this is conservative force. All right. So what is a conservative force? See, if you apply a force to a body, right? This is your body. You apply a force. Okay. Don't worry about the direction, nothing. It's a general thing I'm telling you. So let's say you apply a force and this body undergoes a particular, path, which could be, it goes through mountains and it goes through a valley, etc., etc. And then it comes back, you know, after going through this path, right, to the same position it started. So this is its initial position, and the initial position and the final position are same. So XF represents your final position, right? Now, if you note this, what's so good about it or special about this thing is the body took some arbitrary path. What we call this path, if you start from the same point at end at the same point, it's a closed path, right? It's a closed path. So condition number one, if the work you did, all this while you took this body, around this loopy structure, and the work you did was zero. All right. So work done is zero, which is weird, right? So you have put in effort, there has been some displacement, but if you logically think, this is more of distance, right? This whole thing is about distance. Displacement is zero because your final position is same as initial position. So xf minus xi is zero, right? You did not move an inch, right? You just came back to the same position you started from. If you go around a loop, something like this, which we call as a closed path, and the total work you did was zero, you can be very sure that the force you applied, this force you applied is a conservative force. So this is one aspect of a conservative force. Every time you look into a force which undergoes, takes the body through a closed loop, just at a high level, but the work done is still zero, you're talking about a conservative force. So imagine you throw a ball up, right? Gravitational force acts on it, the ball comes down, it reaches here, right? So what happens? There was a force here and there is a force here also. But the initial position is this, the final position is this, the displacement is still zero, and therefore the gravitational force which got applied on this, the work done is zero, right? The work done is zero, right? So gravitational force is an example of, so gravitational force, okay, let me just write it also. Gravitational force. This is what happens in a case of gravitational force. You don't have any work associated in gravitational force at all. So work done is zero, and gravitational force is an example of a conservative force because, this is also a loop, right? You go up and you come back to the same point. This is like a loop because you came back to, this is a more of real life example. This is more theoretical in nature, right? Just to help you understand. and get your head around the concept of conservative force. So this is one condition for conservative force. Let's talk about another situation, right? Which will mean the second condition, which will help you identify a conservative force. So let's say you have a block, again, and you apply a force. Don't worry about the direction. It can be any direction, right? You apply a force on this block, which is of mass m. And now we have to understand what is the second reason you would call this force as a conservative force. So this is what you did. You started from point A, and this time there is no loop, okay? We started with a closed loop. This time there is no loop. You started from point A, you landed at point B, then you took another path, then you took another path, and then you took another path, right? So hypothetically, you started with 1, this is 2, this is 3, and this is 4, right? So 1, 2, 3, 4, right? You started with A and you ended up at B, okay? So what is the key message? Now, if you calculate your work done here to be some value, okay, let the work done be W1 because it's path 1. Let the work done be in path 2 be W2. Let the work done be W3 in path 3 and path 4. These are all random paths. So don't worry about the structure I've made, which is somewhat wavy in some case, a curve, and some sort of wave here. Don't worry about it. This is something hypothetical, could be arbitrary, anything. And this is a work number 4, which you do when you go through the path 4 from A to B. Now, this is the surprising part. The work done from A to B is equal to work done is equal to work 2 is equal to work 3, right? This is what is astonishing. If you come across a situation where a force is applied on a body and the work done is same irrespective of the path you take, irrespective of the path you took, right? If you find this, the force you applied is again conservative force. I hope this makes sense, right? Take a while to understand this. So you go through 4 paths, and 4 is just a number. You could have 1,000 paths. If you get the same work done in the 1,000 situations with the same force, you take different paths, those 1,000 paths, each one of them different. It could be as random as this, go like this, go like this, go like this, and you still realize that W5 is same as W4, right? Such a force will also be called as a conservative force, right? So there are 2 conditions we talked about. First condition is if in a closed loop, right? If you have a closed loop, you don't do any work. The work done is 0. That's your situation number 1 to be, satisfying the condition of a conservative force. The second condition for a force to be, a conservative force is that it is path independent. So let's use correct physics word. It's path independent. The work done when you apply a conservative force does not depend on path when you take the body from one place to another place, right? This is not a closed loop. So you could, come across situations where both the conditions are applicable, where one of the condition is applicable, and you should be immediately able to point out whether this is a conservative force or not. Obviously, if you have a closed path, you're not moving from one place to another, right? So these 2 are mutually exclusive conditions. Either one of them will be true depending on the path. In one case, you have a 0 displacement, the path is closed. In the other one, you still have a path. It's not a case of 0 displacement. There is a path, but the work done you get across all the paths is equal. And therefore, we will say that the force is conservative in both the cases. I hope this makes sense to you. Now that you've understood what's a conservative force, you've also understood the example of gravitational force. The second example I can give you for a conservative force is an example of a spring, right? So you attach a mass to it, it gets compressed, the whole energy gets converted into potential energy, comes back, stops here, again potential energy, middle of it, it's kinetic and potential, but there is no loss of energy per se. The spring force, which is the restoring force, is also an example of conservative force, right? So if you come back, the energy with the block is same as it was when it started the journey. It started the journey and then it came back. There is absolutely no change, right? So two examples, two different conditions, both resulting in identification of conservative force, right? Now let's talk about this numerical. And through this numerical, which is this numerical, let me just change the color of the pen. What you will find is that you will understand the second concept, which is non-conservative force. Let's analyze this. So you have a force, it's a single force. The body always moves from A to B, but it takes, three different paths. There are three different paths. Path number one, let's label it 1, 2, and 3. Now, remember, it's moving from A to B. So the condition of conservative force we're referring to is this, right? In this particular case, you move from A to B. Now, if you move from A to B, and this is what you need to do, right? It's you have to calculate what are the works which are done, and you have to find whether the work done is independent of path or not. So let's analyze one. In the case of one, situation number one, this is what is happening. What's happening in one is pretty typical. What you have is the work done is minus 60 joule. So probably the body has lost on kinetic energy, minus 60 joule. Second is something like frictional force. Let's put it this way. But for the sake of this numerical, it's some force. If we don't know the nature, we are only interested in finding out whether it's conservative or non-conservative. So let's talk about second. W is equal to 60 joules. Okay, this is W1, this is W2, right? 2, and then W3. W3 is equal to 60 joules, right? As simple as that. If you see, do you think this condition is being met? Is W1 equal to W2? It is, right? But is W2 equal to W3? Sorry, W1 is not even equal to W2. So you have, path dependence, which means the work which is getting done is path dependent, because the work done, the W1 and W2 are not, don't get carried away by W2 is equal to W3. This may give you a sense that, two of the work dones are same, and therefore the force is conservative. It is not conservative force at all. The force we are referring to as conservative should have all the three work dones in this particular example to be equal. That means all of them should have been plus 60 or all of them should have been minus 60 respectively, right? So I hope this made sense. Any force, friction, for example, is a classic example I told you in situation number one, where friction, if you take different route on a friction, for example, this whole ground is a friction ground, right? There's a lot of friction here. You move from this place to this place. Take this route. Apply the same force, or maybe try to move forward. The friction is acting. Move from this to this using a different route. Maybe go out of the ground, come back. In each of this, the work done will be different because the frictional force in each one of the situation is different, right? Therefore, we can't say that it's a path independent situation. The work done depends on the path. If the work done depends on the path, the force has to be non-conservative. I hope this made sense to you. I'll be away for a few days and I'll be back shortly after a gap of 2-3 days. Just bear with me. I have some personal work to do. Once I'm back, I will make some more videos and solutions for you, give you more explanation. In the meanwhile, I urge you to please go through all my videos, previous concepts, go through mechanics, go through kinematics, motion in straight line, go through projectile motion, beautiful explanation. The difference between my channel and any other channel you will see is the explanation part of it. I could have straight away solved this question, but the way I've chosen to approach my learning, or so to say teaching, learning is for you, is through the way of explaining you things. Unless you understand physics, it's hard to get through. And I think explanations, the more you, and one of the things I want to share with you from my experience, I was not like a genius in physics. I was a very, ordinary kid. The way I, mastered physics, and I still say I have not mastered it, but definitely, I have attained some accomplishment in physics. Uh, is the key, which is the key of repetition. So I do the same concept again and again. I keep on testing myself against multiple problems. That's how you develop the skill. The key is in repetition. The key is not in being a genius, right? So go with this key. Wait for me. I'm going to be back after 3-4 days. Keep revising my previous videos. You have plenty of material to watch, so don't worry about it that I'm away for a few days and stuff like that. So thank you very much for your time. Really appreciate it, and look forward to meet you guys very, very soon. Have a great weekend, and see you on maybe Tuesday or Wednesday. Thank you.